Welcome to a lesson. Oh, let's take a look at how we can diagonalize this matrix by using kernels. So what we're going to do, first of all, is compute the characteristic polynomial. So x is down the diagonal minus this matrix. That would give us x plus 1, -2, -1, and the rest. And let's see, and then we have a -1 there. That's 0. 0, 0. Okay, so we compute the characteristic polynomial. All right, so we can do this via a cofactor expansion along the first column here. We can say x times the determinant of this piece right here. So that would be x times the determinant of this piece is, so x times that is x squared plus x, and then -2. Okay, and the determinant of this with a negative sign times what's kitty corner to it, well, that's just 0. So we're good there. So it's just this. All right, so we can just factor this guy right here. And so we're gonna have a 1 and a 2. So we should have a, and we'll have an x minus 1, x plus 2. Right, and that works. Okay, so that's the characteristic polynomial. Now, one thing to note, this characteristic polynomial is also the minimal polynomial of this matrix, because the minimal polynomial has to share the same irreducible factors, and but it can't have any factors raised to a power. So really, I mean, more than one, and it's precisely what we have here. So this is the minimal polynomial. Okay, now this also tells us that what the eigenvalues are, what makes each factor equal to 0. So so we have an eigenvalue of 0, and I'll put this in a diagonal matrix. We can of 0 right here, and from this guy we have 1, and from this over here we have -2. Okay, let's call this matrix A. And what we're going to do is we're going to find a matrix U such that U inverse A U is equal to D. All right. And this U is going to correspond to these eigenvalues. What we're going to do is we're going to build a matrix such that the first column is an eigenvector for that eigenvalue. The second column is an eigenvector for this eigenvalue of 1. And the last one is an eigenvector for that eigenvalue of -2. So how are we going to do this? We're going to do it by kernels. So what that means is this eigenvalue is going to be the eigenvectors from right here are precisely the um, basis, or you can choose just a vector that spans the kernel of this guy, x. Well, what is x? X is like the matrix A. All right. And the way we came up with this one, right, this thing right here is um, we said like x times the identity matrix minus A. So if we're thinking of x acting as a scalar on vectors and other things like that, then these two guys should be the exact same, because this is x scalar action and we're saying that it's going to be the same as A. So really what we're doing is we're assuming that this is a zero action right here, meaning that A can be thought of as x. Okay, so when I say x, that's going to be A, and I'm going to look at the kernel of the matrix A, and I'm going to find a vector that's in it, and that's what's going to be the eigenvector right here. Now, to find the kernel of this, I'm going to use a column trick, which I've explained elsewhere. So what we have, and I'll kind of show, at least in this case, at least how it works. So the first thing we need to do is put this matrix X into reducible echelon form, which it basically almost is. You just kind of, so for X, you have, so maybe I'll do this like X. Okay, so what is x? X is simply um, this, but I'm going to be putting in reducible echelon form. So maybe move that row of zeros at the bottom, and then really I have it. 0, 1, -1, 1, 0, 2. Okay, the column trick is you look at the non-pivot, you look at non-pivot columns, and then the pivots have an action on the non-zero values. And after you're done, you think of adding ones down the diagonal, and wherever that lands, you add to your result of how the pivots act on the non-zero elements here. So one, since one is in the first column, it'll kind of shoot things horizontally, and when it hits something, what it's going to do, it's going to change the sign of it and move this to the first row, since that was in the first column. But you don't want this action to kind of double act on things. It should only act on one thing, and it shouldn't act on anything else. So in order to get that straight, it's a good idea to actually start at the bottom pivot. Start at the bottom pivot and then go. So this is in the second column, so we'll send it to the second row. It's already in the second row, so I want to keep it there. Basically just change its sign. Same thing here, just change its sign. Then add ones down the diagonal. This just becomes a 1. So -2, 1, 1 is the vector that we want to put here that'll be correspond to 0. Next, move to x minus 1, which is this matrix, thought of as x, subtract 1, well, 1 times the identity matrix, so subtracting 1s down the diagonal. So that would be, so think x minus 1, and you have -1, -1, -2, then you have a 1, 1, 0, 0, 0, 2. Okay, and we put this into reducible echelon form. So we can kind of think right here, this guy become a +1, you can rescale it. And then when it comes down, it'll zero this guy out right here. And these are multiples of each other, so you can kind of think of eliminating this and then putting a plus and a minus there. So we can kind of quickly think how reducible echelon form is obtained. And then we look at the non-pivot, same idea. And really it just changes to, we can even write it out right here, 0 +2 right there. And remember, we're writing ones on the diagonal after we're done. So 1, and then that's a nice eigenvector for that eigenvalue. Now we go to the last guy, -2. All right. So that would be x minus. So then we have, it's x +2 right here, coming from that factor. And so we add 2's down the diagonal. So we have 2, 2, 1, and a 2, 0, 0. Then we have a 1, 1, 0. You think about putting this into reduced echelon form, it's pretty similar. That can become, we can rescale it to a 1, and then it can come down and get rid of that guy right there. These are multiples of each other. So we can kind of think about, if you want, just remove the bottom row and just change these guys to 1s. And there we have it. Same idea. You can see it'll become a 0, -1, 1. And then we're done finding our matrix U, which will diagonalize this matrix when we multiply it out and give you this. I mean, we can even double check if we wanted to. We could matrix multiply A and one of these columns and see if we really just like this column, the effect should be just multiplying -2 to that column. Let's see if it works. Okay, so matrix multiplying A to that column is the same thing as saying 0 times the first column, -1 times that column, 1 times the last column. So really taking the last column minusing that guy. So it's 2, -2. So 2, -2. Hey, that's the exact same thing as multiplying -2 to that column. It works. So this is an eigenvector for that eigenvalue. Okay. Anyhow, so that's it. We've been successful at finding our matrix D and U, and then you just need to go ahead and find the inverse there, and this will work. Thanks for watching.